Well, I want to do another one with you. I'm going to go just a little bit faster this time. But what we want to do is find the shear and moment at point C, which is right here. And you can see that we're looking for that. So the first thing we do is find our reactions. First thing we have to do here, because there's a distributed force here, is we need to find out the resultant of that distributed force. So that R here, you can see that this is 9 times 3, so that's going to be equal to 27. And then I can sum the moments about any point to find the reactions. I have an AY and a BY. All right, so let's do that. Sum the moments about A is equal to 0. So I've solved this here. I've got this 12 times 1.5. The 27 has got that lever arm because that's sitting right in the middle of that distributed force. And then BY over here, and I can solve for BY and AY right there. Okay. Now, how do I find out what's going on inside this beam at C? Let's draw a section. Again, I'm going to draw this section just like this right down there. Let's draw a free body diagram of the left side. Okay, so here's my little section line like that. Let's draw the forces. I have an AY, got a 12. Now here is where the distributed force starts. It's going to have the same distributed force value for as long as it lasts, but what I have is this 9 kilonewtons times 1.5. So it's a little smaller value. It's 9 times 1.5, which is actually 13.5. And that 13.5 acts right in the middle of that piece of the distributed force. And it's going to have a lever arm, or a point of application here. So that's going to be equal to 3.75. In other words, it's going to be this 3 plus half of this, so it's right in the middle of there, 0.75. Okay, on the right hand side, to keep this piece in equilibrium, I have a positive shear, and that's going to be at point C, and a positive moment at C, and those are my unknowns for right now. Alright, so let's sum the forces in the y and see what we get. Sum of the forces in the y is equal to 0, so I got AY minus 12, I guess I should label that 12, minus 13.5 minus shear is equal to 0. So in this case, shear is equal to negative 9.75. And again, like I said before, do not change that from a positive to a negative. Keep it as a negative because we need to know whether it's going to be positive or negative when we get to graphing. All right, how about that moment? Let's sum the moments about A. Again, you can sum the moments about any point. Our textbook suggests that you sum the moments about here, and that's perfectly reasonable too. Sum the moments about A. So I got minus 12 times 1.5 minus 13.5 times 3.75 minus the shear times 4.5 plus the moment at C is equal to 0. Plugging this shear into right there and solving for the moment, I got moment at C is equal to 24.75 kilonewton meters. And that is positive in the way I drew my arrow, so that's an appropriate amount. Okay. Should I get the same on the other side? Well, let's go ahead and draw the free body diagram and write the equations and see what we get. So here's my little free body diagram. I have a distributed force here. I have BY over here. The distributed force, again, looks similar to this side. Over here I have 9 kilonewtons times 1.5, and it's going to act right there in the middle. So that's going to be 13.5. And it acts at a very short distance here of 0.75. All right, what keeps this in equilibrium? I have positive shear, positive moment. Those are moments in shear about C and moment about C. And so writing the equations. Okay, so I finished the equations. You just sum the forces in the y is equal to 0. So I got VC, negative 13.5, and BY. I've got a value for BY, solving for shear. And again, I get the same value as I did before. Sorry about that. Let's go back here. And then sum of the moments about any point, and I sum the moments about B over here. Whoops, sorry. Sum the moments about B. I got positive 13.5 times 0.75, then negative shear times that, negative moment, and I get the same value, 24.75. Well, the analysis of triangle loads is often pretty important. And let's say we have a beam here that is subjected to a triangle load, and we want to find out what's going on in the at point B here. We know that we're going to have to draw a little section and draw a little free body diagram, which may include that portion of the triangle load. And in order to do that, we need to find out often the height here of the little portion of the load that we want to consider. So let's call this height y and the total height h. Let's say that y occurs at a distance x, and perhaps there's a total distance or the total length of L. What we can say is that y is related to h in the same way that x is related to L. And so all I do is just write that little ratio. Y is equal to x over L times h. And let's say that y is equal, or let's say that x happens to be 3, and let's say that L happens to be 7. We could say that at that point y is equal to 3/7, or the ratio of 3 over 7, to h, which is 200. And that's newtons per meter, and so I can say that the y value there is 85.7. If you're coming from the right-hand side, let's define some distances here. Let's say that over here if we want to find what happens here at point C, let's say that this distance from the left-hand side is x, and let's say that this distance here is x1. We still have a total height, or a total length of L, but if we're wanting to find that height y as a proportion of h, we could say that if you're coming from the left-hand side, you could say that, if you're coming from the right-hand side, you could say that y is equal to x1 over L times h, which is the same thing, but we can see that x1 is equal to L minus x. So I could say that that is L minus x over L times h. And that's kind of the rule we'll be using is if you got a triangle load, in both this is maybe a little bit easier to memorize. This one should be pretty easy as well. So try to commit those to memory as we go forward. Well, let's go ahead and solve this distributed load problem. We are wanting to find the shear and moment at this point C, right there in the middle. All right, so let's look at this triangle load. First of all, to find the reactions, let's draw the reactions on the page, or say that there's an AY and a BY, and there should be a resultant of that distributed load, or that triangle-shaped load, and you know the resultants are equal to 1/2 BH, so 1/2, the base here is 6, the height is 6, so that's equal to 18, and it acts at a distance of 2 meters right there. Alright, so now we should observe that we have what's left is a trapezoidal shape right here if we draw that section, and we can see that it has a rectangular shape and a triangle shape. So how do I make some sense of that? If I were to look for this height y according to our prior work, previous slide, what we said is that y is equal to L minus x, where this is distance x, L minus x over L times h. So in this case it is 6, which is the length, minus 3 over 6 times 6, and that's equal to 3. So that's not very hard math. In fact, this one is actually symmetrical. It's halfway over there. So if this is 6 here, then if you're only going halfway, you'd expect that that height is going to be 3 anyway. So sometimes they're going to be easy. You can do them by observation. Sometimes you have to set up a little ratio to get there. All right, after that, then we have our triangle shaped, and what we're looking for is how to solve for shear and moment here. So let's draw our free body diagram. What I have is this rectangular load. I got a resultant here that's going to be BH. This resultant here is 1/2 BH. This is going to act at a distance 1. This is going to act at a distance 1.5. AY I've already solved for. Positive shear going down, positive moment going in this direction. All right, how do we get there? Sum of the forces in the y is equal to 0. AY going up, negative R1, negative R2, negative V, and negative shear, and we felt for shear is equal to negative 1.5. Summing the moments about any point, and I generally tend to do it about A, but I got R1 going in this direction times 1, R2 times 1.5, V shear times 3, those are the lever arms, plus the moment about C, or moment at point C, and I can solve that for moment at C. We can also do it from the other side. And again, what we do is we draw positive shear, positive moment. In this case, we have a smaller, probably easier to calculate triangle. So in some cases, it might be beneficial for you to go from the left-hand side. Sometimes it might be beneficial to go from the right side. So you can choose by your convenience and go either direction. It doesn't really matter. But obviously sometimes one is easier than the other. Here I have, again, that height is going to be 3, so in this case the resultant of that little shape will be 1/2 BH, where that's B and that's 3, so that resultant will be 4.5. Got a BY, this resultant acts at 2, got a shear going this way, some of the forces in the Y, got positive V, positive shear, positive BY, negative 4.5, and you get shear is equal to negative 1.5. Sum the moments about any point. I'll sum it about B, and you can get the moment is equal to 13.5. Again, same answer, and it doesn't matter which side you approach it, or from which side you approach it. Well, I want to do another problem with you, and this one is a fixed support. And we've done fixed supports before. But in this case, there's a reaction here that we have to take into account. So we've got some distributed loads here. We've got a pushing force here. Let's draw the reaction that we know of. There's going to be an AY. There should be an AX. And because this is a fixed support, there's going to be a moment, a resisting moment at A. To find those reactions, we get started here. We're going to say some of the moments about A. We'll include that moment about A, which is unknown. It's going to have some distributed forces. Let's go ahead and put the R's here. I'm going to say that there's going to be an R1, which will be this distributed force here, which would be base times the height, should be 24. And there will be an R2 at 1/3 of the way off of there, and that's going to be 1/2 BH, so it'll be 1/2 of 3 times 8, so that should be equal to 12. Again, back to our reaction equation. Some of the moments about there, you get R2 times, and this would be 7. It's going to have 2 components. This 40 kilonewton force is going to have 2 components. It's going to have a 40 cos 60 and a 40 sine 60. And you can see that the lever arm for that 40 sine 60 is 9.3. Some of the moments, you get moment about A is 55.2. Some of the forces in the Y, you get this. Some of the forces in the X, you get that. All right, let's go to the section. If I want to find out what is going on at point C, I have to include, I draw the little free body diagram of that little section. I find out that there's a sub portion of the distributed force, and I'll call this 3 meters, and the loading is 8, So that's going to be 24, and it's going to occur at a point 1.5. It's going to have that moment about A and AX and AY and positive shear, positive moment. So let's sum the forces. Sum the forces in the Y, and I got AY minus 24 minus the shear, and I get shear is equal to 70. If I want to find out the moment about C out here, this is the bending moment. Sum the moments about any point. So I'm going to sum the moments about point A. So I have my moment about A already defined, and that is 550. Then I got negative R3, or this resultant of 24 times 1.5, negative shear times that distance, positive moment going in that way, and I can solve for the moment is equal to negative 302. Often we can, I'm not going to say ignore, but most in these shear and moment problems, we are not often concerned about the normal force. It's in there for completeness, and sometimes I suppose we will need to understand it, but most of the time the shear and the moment are the things we really care about.